Hello everyone, this is Amir Mohammad Dareini, graduate student of Mechanical Engineering, Solid Mechanics. And today I'm going to present a lecture on data-driven modeling of an elastomeric bushing system under various visco-hyperelastic deformations, which was studied by Amir Mohammad Dareini and Mustafa Bagan. In this work, we actually present a new method in capturing non-linear time-dependent behavior of rubble-like materials and elastomers actually. And in the following slides, we discuss the issues we solved and the problem we faced during this work. So let's continue. In this slide, you can see the contents of this presentation. This presentation consists of 6 parts, which are introduction, literature review, methods, results, conclusion, and references respectively, and we will go through each part in the following slides. Now let's continue to the introduction section. Introduction is one of the most important sections in this presentation. In this section, I'm going to talk about 4 important issues. First, I will talk about elastomers or rubble-like materials. Next, I present an introduction on constitutive equations. Then I proceed to research objective and model verification. So let's talk about the elastomers. During the last decade, elastomers or rubble-like materials have been widely used in various industries such as automotive industries and civil industry to produce some devices like elastomeric bushing, structural bearings, and vibration isolator, which you can see them in the picture. The first picture is an elastomer showing elastomeric bushings. The next one is structural bearing, which contains of 2 metal surfaces filled with an elastomer. And the last one is a vibration isolator. Actually, nowadays, this kind of materials used in most fields from automotive industry and civil industry to medical application, and that's because of their unique features like ability to undergo large deformations and retaining their initial shape after unloading. These features drew much attention to this kind of materials, and lots of experiments and works conducted on these materials to find out the constitutive equations which can accurately predict the behavior of these materials. In the subject of constitutive equations, I should mention that since one of the most important issues in solid mechanics has become predicting nonlinear behavior of materials like elastomers, lots of constitutive equation forms have been proposed in the literature, like as you can see here, the Neo-Hookean or Ardo-Boyce model for hyperelastic materials, and Pruni series or EXP model for visco-hyperelastic materials. Constitutive equations are general forms which can be used to predict and analyze hyperelastic and visco-hyperelastic behavior of materials, but as you can see in this slide, these equations always consist of some unknown parts. For example, in yaw form, which is the last one presented in this slide, consists of 3 unknowns, C1, C2, and C3, which must be assigned by utilizer before using. It's worth to mention that here I1 and I2 are invariants, the first and the second invariant of C matrix respectively. In order to determine these unknowns, which are known as materials coefficient, one must run an optimization procedure called calibration process, which is a complicated and important process, but this presentation does not aim to go through detail of calibration process, but you can find detailed information on calibrating material models in the literature. Now let's talk about advantages and disadvantages. There are several advantages and disadvantages in using constitutive equations. Constitutive equations can accurately predict the nonlinear behavior of materials, and also these forms are defined in finite element software as such as Abacus CAE and COMSOL, and you can easily use them. For example, you define a hyperelastic material in Abacus and you choose the form no Hookean, and you can give the for example software the material coefficients and easily use the model. But despite their positive features, there are some disadvantages in utilizing them, like high computational costs both in calibration and prediction process. And the other obstacle we face in this actually concept is the complexity of the formulae, and that's why we really think of this work. In order to control dimension limitations, I mean the limitations we discussed about them in the last slide, this study was carried out and it aims to introduce an alternative way to simplify this procedure and decrease the computational costs and time. Due to their generality and their low computational costs, data-driven methods are promising candidates to capture complex, time-dependent nonlinear behavior of materials. In the following section, we will discuss the various data-driven methods like DMD, DMDC, and neural networks, which are the three methods we use in this work. Actually, there are lots of models available in the literature, but according to some advantages like the generality and simplicity, these three models has been chosen. These models, as I said before, are DMD, which stands for dynamic mode decomposition, with control, or in abbreviation DMDC, and neural networks. In the following sections, we will discuss the formulae and the algorithm underlying these models. And this is the last slide on introduction, and I'm going to talk about model verification. In order to examine the capability of introduced data-driven models in reproduction of the visco-elastic and actually hyperelastic and visco-hyperelastic behavior, nonlinear behavior of material in general, 4 problems are presented in this paper. First one is comparing the output results from a one-dimensional viscoelastic constitutive model, which is Berger's model. I will talk about it later. 2. Predicting the behavior of a hyperelastic material subjected to uniaxial and pure shear loading based on experimental results from the paper, the book published by Trellor, and comparing the result obtained from data-driven methods with analytical results from the literature. Comparing the results obtained from data-driven methods against the experimental results borrowed from a paper published by Lyon, an analytical method presented in the literature on visco-hyperelastic behavior of materials subjected to uniaxial loadings at differential rates and at different rates. And the last one is reproducing the results from the experiments run by Jennifer Kadlewek and her co-workers on the behavior of elastomeric bushings under uniaxial displacement and torsion using data-driven methods. In this section, I'm going to present some previous works in fields we currently working on. Literature review here splits to 4 subsections. In the first subsection, I'm going to present works I've done on constitutive equations. Then I proceed to introduce some references which provide us with experimental results. Then I will talk about some works on data-driven methods, and at the end I'm going to talk about some papers on elastomeric bushings. There are lots of constitutive forms presented in literature like Ogden model, Mooney-Rivlin model, and Arda-Boyce model, which can be used to capture hyperelastic behavior of materials. In present study, as I said before, we did not present details of these models, but for more information, you can see Chapter 6 of Nonlinear Solid Mechanics, a book by Hosoffel, which provide detailed information on constitutive modeling. Also, Shoja Ifard and his co-workers in 2020 published a paper on large deformation of hyperelastic thick-walled vessels under combined extension torsion pressure, analytical solution, and FEM, which can be helpful in this field. And to gain a background on predicting behavior of visco-hyperelastic materials, you can see Khaja Said and his colleagues' paper on finite strain numerical analysis of elastomeric bushings under multi-axial loadings, a compressible visco-hyperelastic approach, which is published in 2013. In this slide, I'm going to talk about some papers on hyperelastic and visco-hyperelastic behavior. As I mentioned before, in the case of experimental data, we used Trello results for hyperelastic materials. He ran a set of experiments on a hyperelastic specimen subjected to uniaxial and pure shear deformation. Also, we use results from lion experiments on a visco-hyperelastic material. He ran his experiments with 4 different scenarios, and we will talk about these experimental results in the following. In this slide, I'm going to talk about data-driven methods. The data-driven models we use in this work are borrowed from data-driven science and engineering, machine learning, dynamical system, and control written by Broughton and his co-worker Kutz. They used these models to solve some problems, such as predicting chaotic behavior of Lorentz system, dynamic behavior of a fluid around a cylinder, and also in image processing. DMD and DMDC algorithm have been introduced in a book published by Kutz and his colleagues known as Dynamic Mode Decomposition, Data-Driven Modeling of Complex Systems. These models apply to some problems such as unstable system with a proportional controller stabilizing the system, and a high-dimensional stable dynamical system with exogenous forcing. Now let's talk about elastomeric bushings. Elastomeric bushings are essential components in tuning suspension systems. These bushings isolate vibration, reduce noise transmission, accommodate oscillatory motions, and accept misalignment of axes. These bushings usually are made of a hollow elastomeric cylinder contained between 2 cylindrical steel sleeves that connect components of some suspension system. The use of these bushings reduces shocks and vibration. In general, these bushings undergo radial, torsional, and axial deformations. As I said before, the main goal of this work is to predict the behavior of visco-hyperelastic materials like elastomers, especially bushings, under or biaxial tension, compression loading, as well as shear loading, using different data-driven approaches. To the best knowledge of the authors, this work is the first article in this area. In recent decades, some papers have been published on bushings behavior. For example, Atkins and Gent in 1954 actually, excuse me, studied the response of elastomeric bushings under small deformations. Morman and his co-worker Pan investigated the axial radial response of the bushings by comparison of the analytical solutions with finite element results in 1988. Weinman and co-workers proposed a force displacement relation for the bushings, including viscoelastic effects, in 1998. And one of the most important references in this work, Kadlovec and co-workers in 2003 ran some experiments on bushings. Their experiments were performed on a set of axisymmetric mold-bonded bushings under 1 millimeter uniaxial displacement and 15 degrees torsion subjected to the sleeves. A computer-controlled Instron 8511 multi-axis servo hydraulic test machine was used to perform quasi-static and dynamic displacement control tests on the samples. They used the ramp loading in both uniaxial displacements and torsion. The results were reported in two different systems: radial force related to uniaxial displacement and moment related to torsion. In this slide, you can see the procedure we follow. First, we collect data from our sources, which are results obtained from literature and numerical solutions. Then we split those data into the two data sets: training data sets and validating data sets, as you can see. I should mention that we cannot use same results for these data sets. Training data set and validating data set are not the same. As you can see here, X is the output of the system, and U here is not actually the input. It is an arbitrary library of inputs. For example, consider a matrix which its columns are, for example, the inputs power 2, exp of inputs, and etc. Actually, U here is an arbitrary library of inputs, which can consist of inputs in polynomial or exponential terms. It's worth to mention that there is no limitation in this library, and one can use any terms in it. Actually, you can just use input, but when we use just inputs and we didn't actually use the, for example, polynomial terms of inputs, the accuracy decreases, and for the sake of accuracy, we actually use these arbitrary libraries. Next, we break datasets to U and U prime, as well as X and X prime, which U prime and X prime are one step ahead of U and X in time. The first step in using any model is calibration. We use training datasets as well as an optimization command, for example, fmincon or lscov or anything in MATLAB to calibrate our model. In the following slides, we present the formulae and discuss about calibration process. After calibrating, we need to validate our model's efficiency. In order to do that, we ran a cross-validation process, which cross-validation process means we did not use validating dataset in training dataset, and these two datasets are not equal. Let's continue to the next slide. In this slide, you can see the main formulation of DMD as equation 3. Here, the main goal is to find matrix A. As I mentioned before, we use an optimization command in MATLAB like fmincon, lscov, or GA to calibrate our model, which here means finding matrix A. We can present DMD formulation in the form encountered in equation 4 if we assume uniform sampling in time. As you may notice, there is no control value in DMD algorithm, and actually there is no input dependency in the algorithm. This model predicts the response of a system just based on response on the last time step, and this limitation leads to an inaccurate prediction. Dynamic mode decomposition with control, or in abbreviation DMDC, had been introduced so as to solve this issue. In this slide, you can see the main formulation of DMDC. The main goal here is to find matrices A and B. It's worth to mention that we assume uniform sampling in time, and the calibration process are same in DMD and DMDC. And you can see the difference between DMD and DMDC in the figure 1. Actually here we don't have two matrices, matrix A and matrix B. Actually we have a larger matrix, and as you can see here we use X in K, actually in time step of K, and U in time step actually equals to K plus 1. That means actually for predicting the behavior of a system in the current state, we use the response of the system in the last time step and the inputs, actually the library of inputs in current state. So it's for DMDC. Let's continue to the neural networks. So next slide is about neural networks. Due to significant leaps in computer science in the last decades, machine learning has become one of the most crucial topics. There are many methods in machine learning, but the primary focus of this work is on neural networks, and that's because neural networks present a robust model that can predict a nonlinear system with great accuracy. There are many neural networks type, various neural networks architectures actually, which are available in the literature, such as cascade neural networks, feed-forward neural network, and etc. But in this study, one of the simplest types, feed-forward neural networks, has been used. Feed-forward neural networks, which are actually shown here in figure 2, have input and output layers along with hidden layers containing some nodes, which their number is describing by the user. Here H1, H2, actually H11, H12, H13, and etc. and H21, H22, and etc. The number of them are described by the user. For example, the user set the number of hidden layers and hidden nodes. For example, this network has 2 hidden layers and in each of them, in each of hidden layers has, for example, 10 nodes. Let's continue. As you can see in figure, inputs move toward outputs by multiplying by weights, adding a bias, and going through an activation function. Weights and biases have determined during calibration process, and activation functions are predefined functions such as log-sig, and also called sigmoid and or etc. It's you can search them on internet. Actually, activation functions for neural networks, and there's lots of functions like them. Yeah. Now let's see how neural networks work. In neural network, training and predicting are two separate processes. Initially, a neural network is formed by setting the number of hidden layers, the number of nodes in each layer, setting the activation function, and also training method. Then a dataset consisting of both inputs and outputs are given to the network. The network will then train itself to find appropriate weights and biases in order to match its output with the data. Now it's ready for predicting process. In predicting, some other inputs are given to the network and it automatically tries to find the output. In this research, the deep learning toolbox in MATLAB has been used to train the networks and gain results. This work employs two approaches to train the networks: the Levenberg backpropagation approach and the scaled conjugate gradient backpropagation. And also you can see the general formulation of neural networks in figure in equation 6. As you can see, the response of the system in current state is based on the response of the system from the last time step and library of inputs in the current step, as DMDC has the same link. Okay, let's proceed to the next one, to the next slide. Now let's see some results. The first problem we solved using data-driven methods is a one-dimensional visco-elastic model presented by Burgers, which depicted in figure 3. You can see the main formulation of this model in equation 7. In order to obtain training and validating dataset, we solve equation 7 using ODE 45 command in MATLAB. Here, sigma, sigma dot, and sigma double dot stand for the stress and its derivatives in time. Epsilon dot and epsilon double dots are derivatives of strain in time. EIs stand for the spring stiffness, and eta i's denote the dashpot coefficient, respectively, which should be defined by user. So in the next slide, I'm going to present the result obtained from MATLAB and the result we gained from our models. Now let's continue. In this slide, you can see a comparison between analytical results obtained from solving equation 7 by MATLAB and data-driven methods. As you can see, data-driven models can accurately predict the response of the system and follow the loading path. By solving this problem, we actually decide to continue our work, and it turns out that these models will work. Now let's see other problems we work on them in this study. second problem we solved is predicting behavior of a hyperelastic material under uniaxial tension and also pure shear. In this set of problem, we use result obtained by Trello and we compare result gained from data-driven models against four other constitutive models available in literature, which are EXP-LN model, Ordo-Boyce model, Mooney-Rivlin model, and also EXP-XP model. You can see the material coefficients related to these models in our paper. In this problem, we use experimental data obtained from uniaxial extension test to train our models, and then through a cross-validate process, we predict the behavior of material under pure shear loading condition. In the figures, training and validating datasets are pointed out by triangles and circles respectively. As you may notice, in case of data-driven models, there is a great accordance between experimental and predicted results. In the last, it's worth to mention that in this problem, we used a single layered feed-forward neural network, and the library in this problem consists of inputs as they are, and there are no more terms included. Now let's talk about the next problem, which is predicting behavior of a visco-hyperelastic material under uniaxial tension in different rates. These experiments ran by Lyon. As you can see in figure 6, we break the whole dataset into the two spare datasets, training dataset and validating datasets, which pointed out by triangles and squares in the figures. And it's worth to mention that the U matrix here is just input terms as they are, just like the previous problem actually. And as you can see here, there is a great accordance between data-driven models and results gained from the experiments. So let's go to the next problem. In this slide, we are going to investigate behavior of the visco-hyperelastic materials in unloading situation, and also examine the ability of data-driven models in predicting the visco-hyperelastic behavior of materials under loading and unloading deformation based on experimental data published by Ghorbanoglu and his co-workers performed on a self-healing hydrogel. Similar to the previous problem set, two different data sets are needed for training and validating. Experiment of Ghorbanoglu and his co-workers consist of two parts: loading and unloading performed at different rates. For this set of experiments, a constant loading rate of 0.3 per second and three unloading rates of 0.001, 0.01 and 0.1 per second were chosen. In this section, models are trained on the results obtained from experiments with unloading rates 0.001 and 0.1 per second, and then through a cross-validation process, the results for experiment with unloading rate of 0.01 per second is obtained. In this problem, the inputs are strain and stress from the previous time step. The library includes these terms up to the order 3, and the output is the stress in the current time step. The results are shown in figures, and as you can see, the data-driven models can accurately predict the behavior of a visco-hyperelastic material in loading as well as unloading. And now it's time to talk about the last and the most important set of problems we solved in this paper. In previous sections, the performance of the data-driven methods in reproduction of classic uniaxial tests under quasi-static and dynamic loading was evaluated. In this section, the main goal is to train data-driven models to predict the behavior of an elastomeric bushing based on results presented by Kadlovec and her co-workers. The elastomeric bushing used by Kadlovec and her colleagues was made of a hollow elastomeric cylinder embedded between inner and outer steel sleeves, where its dimensions are 60 millimeter length, 18.2 millimeters outer radius, and 9.85 millimeters inner radius. As mentioned by Cadleck, the definitive test for elastomeric bushing is step loading, but as the actual step loading is impossible, a ramp loading was chosen. Multiple experiments were run in different radial and torsional deformation. The maximum displacement, torsion, and total time actually are constant in experiments, which is 1 millimeter displacement, 15 degrees, and 50 seconds respectively. But in these experiments, rates are different. The experiments were run in 5 rise times. I mean how long it takes to reach the maximum deformation. For example, you can see what I mean in the figures, in figure 7 actually. Deformation, actually rise time is how long it takes to reach the maximum deformation in each experiment, including 0.5, 1, 2, 4, and 8 seconds. The results gained from those experiments are dividing into training dataset and validating dataset to train and validate the models respectively, which again pointed out by triangles and squares in the figures. The inputs in this problem are radial displacement, torsion degree, radial force in previous time step, and also moment in previous time step. The outputs in this problem are radial force and moment in current time step. Libraries, U here used in this problem consists of terms as they are like the other problems. And it's worthwhile to mention that the training dataset and validating dataset are the same. I mean, training are the same in neural network and DMDC. I mean, training dataset in neural network and DMDC are the same, and also the validating dataset. I do not mean that training dataset and validating dataset are the same. Training datasets in both models and validating datasets in both models are the same, and results obtained from neural network and DMDC are shown in figure 7 and 8. That's it. In order to predict the visco-hyperelastic behavior of a material, considering the loading path is very critical. There are two essential characteristics of the time-dependent behavior of materials that are coupled to the loading path: the maximum amount of force or moment. You can see this in the figures, and the equilibrium or relaxed amount of force or moment. You see in the end of an experiment. You can see it in the figures. As depicted in figure 7 and 8, the data-driven models, neural networks and DMDC can predict the relaxation response of elastomeric bushing in different deformation modes. As mentioned, the maximum force or moment is a vital characteristic in the relaxation response, indicating that a model can accurately follow the loading path. As you may notice, data-driven models accurately predict the maximum radial force and moment. Furthermore, the relaxed behavior of elastomeric bushings is successfully predicted. In this slide, I want to answer a major question. Why should we use data-driven methods? And the answer can be, as the objective function is nonlinear in models related to nonlinear materials, the calibration process is complicated and computationally complicated, computationally expensive, and time-consuming task. While in data-driven methods, one does not face these challenges since these models are simple and they do not involve a high computational cost. Another reason to think about these models is their unbelievable speed in reaching a response that is not comparable to numerical and analytical methods. As well as the positive aspects mentioned here, there are some limitations in these models. For example, there are some difficulties in implementing these models in FEM software such as Abacus or COMSOL. And another limitation of these models is that they have some limitation in predicting a deformation regime that has not been present in their training dataset. And also these models require a quite rich training dataset to offer a good performance. And that's it. In this slide, you can see some major references we use in this work. Actually, for more information, please see the article. And this was my presentation. Thanks for your attention, and if you have any questions, feel free to contact me through my email or my cell phone number on WhatsApp or Telegram. You can get in touch with me. Thanks for your time, and good luck.